Crystallization is a powerful technique for purification of solid organic compounds. The compound is dissolved in hot solvent and the solution is allowed to cool. If done properly, only crystals of the desired compound will crystallize out of the solvent, and the chemist has only to filter the solvent from them to obtain the purified compound. Before you begin a crystallization, you must choose the proper recrystallization solvent. Ideally, the compound should be very soluble in the hot solvent and only slightly soluble in the cold solvent. The diagram illustrates the amount of a hypothetical compound that can be dissolved in 3 solvents, A, B, and C, as the temperature of the solvents is increased. Solvent A would be a good crystallization solvent for the compound because the compound is very soluble at high temperatures, while only slightly soluble at low temperatures. Solvent B would not be a good solvent because the compound is very soluble both at high and low temperatures. Solvent C would not be a good solvent because the compound is not soluble in it, even at high temperatures. Crystallization must be allowed to proceed slowly. In a proper crystallization, an equilibrium is established between molecules in solution and molecules in the crystal lattice. A molecule will tend to become attached to a growing crystal if the crystal is composed of the same type of molecules because of a better physical fit. If time is allowed for equilibrium between molecules in solution and molecules in a crystal to be established, only like or suitable molecules will be allowed into the growing crystal structure. If, however, crystallization proceeds too quickly, impurities can be trapped in the structure and a precipitation rather than a crystallization occurs. In a crystallization, impurities are removed at one or more of 3 stages of the procedure. 1. They are insoluble in the hot solvent and are removed by hot filtration. 2. Colored impurities are removed by adding a decolorizing agent and hot filtering. 3. The impurities are soluble in cold solvent and are removed by vacuum filtration. Our demonstrator will show the steps of crystallization. The compound to be purified is benzoic acid, and it will be recrystallized from water. Benzoic acid has a solubility of 0.2 grams in 100 milliliters of ice water and 7 grams in 100 milliliters of boiling water. Consequently, water would be a good solvent for recrystallizing benzoic acid. Our demonstrator will recrystallize a small amount of benzoic acid. It is a good practice to recrystallize only a portion of your compounds in the organic chemistry labs. This saves on both solvent consumption and waste production. Place the benzoic acid in a small Erlenmeyer flask. The literature references state that pure benzoic acid is white. The material we see is appreciably colored, which is a sign of an impurity. Add a boiling chip to some solvent in a beaker and to the Erlenmeyer flask. Boiling chips are small porous stones that contain trapped air, which they release when the solvent is heated. The bubbles of air ensure even boiling of the solution. Heat the solvent, in this case water, on a steam bath. Note that the steam bath is kept warm with only a gentle flow of steam. Add a small amount of hot solvent and swirl the flask. Add a little bit more solvent and swirl again. Note that all of the benzoic acid is dissolving. If our demonstrator had kept adding solvent and observed that no more material was going into solution, she would have suspected insoluble impurities and performed a hot filtration. Now that all of the material is in solution, add a milliliter or 2 of additional solvent to allow for evaporation in the procedures that follow. Swirl the solution and note its color, greenish blue. The material is most likely contaminated with a colored impurity. Therefore, our demonstrator will add some norite, or activated charcoal, and swirl and heat for a few minutes. Norite is a decolorizing agent which absorbs on its surface highly colored materials. Hold the flask against a white sheet of paper or a paper towel and see if the color has disappeared. If it has not, continue heating and swirling for several minutes. If it is still colored, add another small portion of norite and continue heating. If you notice any white crystals of cholesterol at any time during this process, add a milliliter more solvent. When the solution is clear, remove the flask from the steam bath. The norite pellets can be removed from the solution either by decanting or by transferring with a Pasteur pipette. To decant the solution from the norite pellets, carefully pour the solution from the flask into a clean flask, leaving the norite pellets behind. You may want to wash the pellets with a small amount of fresh solvent. To transfer the solution using a Pasteur pipette, place the tip of the pipette against the bottom of the flask. Draw liquid into the pipette, leaving the norite pellets behind. Again, you may wish to wash the pellets with fresh solvent. Place the flask containing the dissolved benzoic acid on the bench top. Do not disturb this flask for the next 15 minutes. While you're waiting for the crystals to form, set up the apparatus for vacuum filtration. Clamp your sidearm flask to a ring stand. Connect your Buchner funnel to the sidearm flask using a cork or rubber adapter. Use a piece of vacuum tubing to connect the flask to the vacuum source. Do not use Tygon tubing, as it will collapse under vacuum. Place a small piece of filter paper inside the Buchner funnel. Pour a small amount of cold solvent through the filter to ensure a tight fit against the holes of the funnel. Crystals of benzoic acid form as the solution cools to room temperature. In practice, occasionally crystals of a compound do not form readily as the solution cools. In these cases, the solution has become supersaturated and crystallization must be induced. One method for inducing crystals is to scratch the inside of the flask at the surface of the solution. Another method is to add a seed crystal, which is a small crystal of the original material. When crystal growth is no longer apparent at room temperature, place the flask in an ice bath for an additional 10 minutes. Turn on the water aspirator. Rapidly pour the mixture through the funnel. Rinse the flask with a small amount of cold solvent. The crystals need to dry for a while to remove any solvent which adheres to them. Usually this is done simply by drawing air through them while they remain in the Buchner funnel. Remove the filter paper from the Buchner funnel and transfer the crystals to a watch glass. Sometimes the crystals are dried in an oven after the filtering process. The purity and identity of solid organic compounds is generally determined by melting point determination. Our labs use either Mel-Temp or Fisher-Johns melting point apparatuses. On the Fisher-Johns apparatus, this is the hot plate, the thermometer, the eyepiece. To take a melting point, place a small amount of crystals between two cover slips. Place the cover slips on the hot plate of the apparatus. The chart on the wall gives the proper setting of the melting point apparatus, assuming you know the melting point of the compound which you isolated. The anticipated melting point of benzoic acid is 122 degrees. Therefore, reading from the chart, the setting of the apparatus will be about 45. To begin, set the apparatus to 100 and monitor the thermometer as it heats up. When the temperature is 15 degrees below the anticipated melting point, turn it down to the indicated setting of 45. Carefully monitor the crystals through the eyepiece. Note the temperature at which they begin to melt, then the temperature at which they have all melted. Mel-Temp apparatuses are used in a manner similar to the Fisher-Johns. This is the eyepiece, the temperature control knob, and the sample holder. The sample is placed in a small capillary tube. To get the crystals into the bottom of the tube, tap it gently on the bench top. Place the capillary tube in the Mel-Temp as demonstrated. Set the apparatus according to the chart in your manual and turn on the digital thermometer. Observe the sample through the eyepiece. Be careful not to touch the post in front of the eyepiece which says, "Caution, hot unit," with your face. The melting point of the sample is 119 to 120 degrees. The melting point of benzoic acid is listed as 122 degrees in the CRC. The narrow melting range and near proximity to the literature value indicates that our demonstrator has successfully purified benzoic acid. When you're finished, place the used cover slips or capillary tubes in the proper container. Place your purified crystals in the recovery jar. Place the wet filter papers in the plastic tray in the main hood. Place any unused solvents in the waste carboys. Do not place filter papers containing crystals in the plastic tray. When the solvent has evaporated, these filter papers are thrown in the trash. To assure proper treatment and disposal of organic compounds, and thus the safety of our environment, they must be placed in the jars and containers as directed in your lab manual. This completes the crystallization procedures used most often in the organic chemistry teaching labs. The procedures illustrated today have been kept intentionally brief. Be sure to read your lab text and lab manual for additional information.